two examples for just incorporating the R and S configuration of a compound while naming using the IUPAC. One thing you should remember is always the prefix which comes first is the stereochemistry of the substituents, meaning that here in the parentheses what you see are the specific absolute configuration of that compound. So they always be in parentheses, and again they will be repeated together with the substituents. But first you have to just put in parentheses the absolute stereochemistry. That's the first rule. So what it tells us is that at 3 position there is a substituent with R stereochemistry. At 5 position the substituent has an S absolute configuration. At 6 position there is a substituent which has an R configuration. So the whole thing in the parentheses refers to the absolute configuration of that particular compound. Here I have a nonane compound. Nonane, as you know, would be a 9-carbon aliphatic chain. So I will have 9 carbons. So I will start 1, 2, 3, 4, 5, 6, 7, 8, 9. So I will make sure that I have 9 carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the question is to draw the structure for 3R, 5S, 6R, at 5 position ethyl, at 3 position and 6 position 2 methyl groups, the dimethyl. So this is very easy. So let me start from here. Carbon number 1, carbon number 2, carbon number 3 is a methyl group. Number 4, I don't have anything. At number 5, I have an ethyl group. That's an ethyl group. At 6th position, I have another methyl group. So the compound at least looks like this to begin with. So we didn't specify any stereochemistry at this point. Remember, everything is flat, and I didn't specify any kind of stereochemistry. But the structure has at 3 position an R, at 5 position an S, at 6 position an R. So this is our 3 position for the metal, which is, it says it's an R. So first, if you just look at them, it is telling you that there are 3 stereogenic centers. Stereogenic center 1, at 5, at 6, at 3, at 5, and at 6 there are stereogenic centers. But we are required to draw with stereospecificity at 3R, 5S, 6R. So how do I write that? So if just I rewrite that again, one, two, three, 4, 5, 6, 7, 8, 9. At 3 position I have metal. At 5 position I have ethyl. At 6 position I have metal. Oh no, that is not 6 position. 6 position is right here. So this is a stereogenic center, this is a stereogenic center, this is the stereogenic center. So to draw this in 3R position, what I will do is the priority, if this is the carbon I'm dealing with, this whole group would be priority 1, right? And this group is priority 2. This group would be priority 3. Definitely, if I am just assume there is a hydrogen, obviously it's not an assumption, there is always hydrogen. So if I put the hydrogen at the back, it would be at the 4th priority, right? That's hydrogen. So I can go, if this is up and hydrogen is down, I can go from 1 to 2. So that is the right stereochemistry to put the metal group up. That will give me an R. So it's just a trial and error way by just doing this up metal group. This becomes an R. That's what I'm required to put. So that's the correct stereochemistry, to put the R group, the metal group, up towards me. How about in this case? So in this case, for carbon, this one, which one is the priority? The priority is this side or that side? I would say it is this side. This is 1. The reason being, if you just go this way, the carbon has 2 hydrogens. But if you go this way, that carbon, which is analogous to that one, has not 2 hydrogens, but 1 carbon, 1 hydrogen. So it takes a precedent. So this would be now 2. So this would be now 3. The implied hydrogen is here, the 4th one, hydrogen. So if I go this way, while assuming hydrogen at the back and ethyl group coming to me, if I go that way, this is an R, but I'm supposed to give a 5s. So what I'll do is making hydrogen up, but the ethyl group down would give me an S. So that's how I would be just drawing an S configuration. So this is S now. At 6th position, I have R. So if the priority obviously is this side is number 1, this side is number 2, metal is number 3. Obviously, hydrogen is somewhere here as a 4th priority. So going from 1 to 2 this way, if hydrogen was at the back, that's how you should go without any switching or anything. If hydrogen is down, I can go 1 to 2 like this. This is a clockwise direction. It's an R. Therefore, my initial assumption to put hydrogen down is fine, because it gives me an R configuration going from 1 to 2. Therefore, this metal group would be up, and the hydrogen obviously is down. So I'll just erase everything, and this is an R configuration. So 3R position, 5S, that's correct, and 6 is R. 6th position is on R. So this is how you draw that compound. First, identify how long it is, put the substituents at the right carbons, and then test whether it is an R or S, whichever structure you start with. I always start by assuming hydrogen down to make it easier, so that I will just take the opposite if it is different out of that. Okay, here I have decane. Decane is a 10 carbon compound, right? But it has only one stereocenter, one stereogenic center, because in the parentheses you have only one at 4th position. It is an R configuration. It tells you that compound has only one stereogenic center. The top one, in the top example, you have 3 stereogenic centers. But the second one has only one stereogenic center with 10 carbons. So let me start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me check again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's 10. So it tells me that there are two substituents. There are two substituents. It should be two stereogenic centers. I'm sorry. So it should be at 4 and 6. So make sure that we have 4R and 6R, because you have 4 ethyl and 6 methyl decane. So there are two substituents and two stereogenic centers. So make sure that I have corrected myself, that there are two stereogenic centers. At 4th position is ethyl. So I will start from here, counting 1, 2, 3, 4. At 4th position I have ethyl group, CH2, CH3, ethyl. That's an ethyl group. At 6th position I have a methyl group. So let me count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the structure at least looks like that. But we haven't specified yet the stereochemistry of those carbons. The stereogenic center are these two. So there are two of them. Two stereogenic center. At 4th position, I have an R. So if the priority counting comes, this will take, for this carbon, this whole chain is larger group, priority 1. This whole group is a propyl group, and this is ethyl. So this will take priority 2. This will take priority 3. Obviously, the implied hydrogen is, it is there, the 4th group. So initially, as I already told you, to solve such problems, it is easier to put the hydrogen, to assume the first initial assumption should be, okay, if I put hydrogen at the back, it is easier for me to go from 1 to 2. So, okay, I put it at the back. Therefore, I'm just going from 1 to 2. This is clockwise. Therefore, it is an R. So my assumption was fine. So this is up. And the hydrogen is at the back. So this is a 4R position. How about for doing for next carbon at 6th position? So this is a 6th position where you have a metal. So this is an R at the 6th position. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So 4 is a priority. So if you just look at this whole group is more prior than this whole group for that carbon. So this is 1 position, 1, priority 1. This is priority 2. This methyl group is priority 3. 3 groups are assigned. Now, like I said, always put the hydrogen, initial assumption, just put it at the back. Okay, see what you get. So if I put the hydrogen at the back position and I'm moving from 1 to 2, it gives me an S counterclockwise. Therefore, my assumption should change that this actually not towards me, hydrogen is back, hydrogen is actually towards me, but this methyl group is at the back. So this is the R configuration. So this is 6R. So this is how you assign naming, the naming. So I will recap again. Make sure that in the parenthesis what you see is the stereochemistry of the compound. And the substituents are just like in the IUPAC convention. That's where the positions are. So the first thing you have to do is write the longest chain molecule first, meaning that no name or decane. So straight chain, and put exactly where the substituents are at 4 and 6 for this case. Once you put them in the right position, make sure that you test if this is up and hydrogen is down. That is always should be your initial assumption, so that you test whether you get the right one or the opposite. If you get the opposite, you change your initial assumption from up to down for that substituent. So this is just, you have to practice a lot. So this is how actually the naming includes stereochemistry as well. So naming in the IUPAC, in the parentheses, you will find that the positions and the absolute stereochemistry of your substituents are given like this. Here you see another molecule, and when the assignment is just to name this compound obviously shows stereochemistry. It's already shown that is the stereogenic center, and the stereogenic center are written as absolute configuration. Their absolute configuration is known. That means it's not ambiguous whether that is R or S, OS or R. So first of all, those are already determined or given to us. So if you remember in IUPAC naming, the first thing is to identify what is the longest chain, especially when it's an aliphatic chain like this. What is the longest chain you want to consider? So if you just look at here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's a 9 carbon compound. So you have all the substituents in one line. So let me just make sure I have the right lanes. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So this is a 9 carbon compound. That is 1, 2, 3, 4, 5, 6, 7, 8, 9. So over the 9 carbon, you have how many substituents? You have 1, 2, 3 substituents. How about counting from here? 1, 2, 3, 4, 5, 6, 7, 8. So that would not be a longest chain. How about this way? 1, 2, 3, 4, 5, 6, 7, 8. So the longest chain is it's a nonane. It's a nonane, not octane. So I have made a mistake on my paper. So it is an octane and a nonane compound. Nonane. That's 9 carbons. So the chain I'm going to consider would be this long chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the chain, I have 3 substituents. So what are the substituents at 1, 2, 3, 4, 5 position? At 4 and 5 position. Okay. Here at 1, 2, 3 position. So you should always consider the one which gives you the lowest numbering where the substituents should start. So 1, 2, 3, 4 metal, that's not where I should start, because if I start from this side, it will give me 1, 2, 3. At 3 position, I have metal, and at 1, 2, 3, 4, 5 position, I have what group? This is called isobutyl. Not isopropyl. This is isobutyl. And at 6th position, I have another metal group. So now I have 3 substituents. My task next to this would be now to just look at what their stereochemistry is. So for this stereogenic center, priority is obviously this is 1, this is 2, this is 3. As I already told you, this is already specified that the hydrogen is at the back of the plane of the board, so I can just directly move from 1 to 2. This tells me this is an R configuration. So for that metal, I have an R configuration. Absolute configuration, R. Okay. Now, for this carbon right here, the priorities are, if you just count for this one, if you just go this way, this is CH2. If you just go this way, it's CH2. But if you go here, it is a CH carbon. So priority would be for this one. But the next one would be, you have CH2, right? So you have CH2, they are equal up to here. When it comes here, you have 2 CH3s, but you have here, you have 1 CH3, another CH2, another CH3. So this would take a precedent, this side. This is 2. So the third one is obviously this one. The carbon is coming to me. It's not to the plane of the board, it is coming to us, because the absolute configuration is already determined. This is down, so 4 is up. So if I go directly 1 to 2, hydrogen should be at the back of the board. So the only thing I would do is an assumption. If I just switch 4 and 3, and 3 comes here, I can directly go like this, 1 to 2, an R. But remember, since I switched it, it is an S, since hydrogen is not at the back initially. So even though it shows an R, by just assuming hydrogen is going down and this one changing this would have been given me an R. But obviously hydrogen is not in the right place where it is down, so it's an S configuration. So that is an S. How about the last one, which is the 6th position metal? So I have 3R. Remember, this is 3R, 5S, and 6th position would be this one. 6 would be now, the whole of this is 1, priority 1 for this carbon. The whole of this is carbon 2, priority 2, 3 is this. So hydrogen is likely, it's already at the back, because if this is up, hydrogen is obviously to the back of the board. So we can easily go without changing anything. We can go from 1 to 2, which is an R movement. So this is R. So 6 is R. So now everything is figured out. Now it's just a matter of writing the whole thing. So now we will start from 3R, comma, 5S, comma, 6R in the parentheses. These are 3 stereogenic center in the parentheses. Now I start naming. So the first thing you have to write is not the metal, you go by alphabets, right? So iso, third, and all that, they don't count in the alphabet naming. Actually, the butyl comes first. So iso, tertiary, those kind of di, tri, those kind of prefixes, they don't count in the alphabet naming, in the alphabetical order. So it's 5 isobutyl, And the next one is 3,6. You can combine them because they are the same kind of substituent, but you have to add dimethyl because you have two of them. Dimethyl, and it is 9 carbon, non-A. So S3R, F5S, S6R, 5-isobutyl, 3,6 dimethyl non-A. So here what we have achieved is just we assigned the configuration 3R, 5S, 6R, and 5-isobutyl, 3,6 dimethyl non-A. So this exercise actually shows you or tries to demonstrate that if you are given an IUPAC name with this kind of stereochemistry already identified, this is not only enough to give the name. You have to give also the stereochemistry of each one of the substituents, because the stereochemistry is well defined to you to assign it. So in naming a stereochemically pure compound, you have to include the R and assignment within a parenthesis with the right absolute configuration. Continuing our work on stereochemistry, this has compounds that are shown as a Newman projection, and the task is to identify what relationships they have, because constitutionally they are the same. So the only thing their differences would be their stereoisomeric, their stereoisomerism, because constitutionally they are all the same. Same chemical formula, they have the same constituents, everything is bonded in the same way as in each one of these cases. So the question is, how is A related to B related to C, or to D? So one thing here is that it will also challenge you to see how a Newman projection works as well. So the problem is the stereoisomerism, and on top of that, you need to change the Newman projection into something you would easily understand. So basically, all of them have two chiral centers, or two stereogenic centers. One is at the front carbon, right here. That carbon is a stereogenic center, and remember there is another carbon which is containing this, that, and this group. So that's also another stereogenic center. So each one of them have two stereogenic centers. One at the front carbon, second one is at the back carbon. So Newman projection shows you two fronts. Now, the way I would resolve this is to know the relationship. I need to assign the absolute configuration of that carbon or of each one. So two stereogenic center, you have to assign two R or S carbons, here the same, and see what relationship each one of them have. So to begin with this one, you always can keep in the front two of the groups on the same plane, one out of the plane, and the other inside of the plane of the board. So the way I will resolve this is by just drawing CHO. This is aldehyde group. Actually, it's written as this. I'm drawing for the front carbon, CHO, and OH in the same plane, and I have H here, and that whole group of the back carbon is at the back. So that carbon contains hydrogen, CH2OH, and obviously it has OH as well. So just I'm just considering this one as the most important one at this point. So what I have here is, this is how I interpret the front carbon and the back carbon to contain. So priority wise, this is 1, this is 2, this is 3, and 4 is this one. So right now, what I'll do is I'll send 4 to the back, okay? And OH comes here. If you just rotation, this is rotation, it doesn't change the molecule. Rotation doesn't change the molecule. So by rotating it to the left, I can redraw this again, keeping that still on the plane and just rotating. OH comes here, hydrogen goes back where I want it to be, and this whole group, group 3, comes on the plane of the board. This is COH, CH2OH, and hydrogen would be on the plane of the board. So still the priority is, this is 1, this is 4 now, where it should belong, this is 2, and this is, I think, 3. So I can easily go like this. This is a clockwise rotation. So this carbon is an R carbon. Do you agree? That is an R. So this is R. The front carbon is R. How about the back of this problem? So what I will do is flipping, rotation, whatever you do on the molecule doesn't change how it is bonded. What I'll do is I'll flip the whole molecule and put the OH up. That way everything would flip. So the OH would be at the top. It comes to the front. I'm just flipping the whole thing. So you'll see this. What you'll see is, if you just flip everything up, OH is here, up, like hold OH and put it back. So you're bringing it to the front. So when you do that, CH2OH would be here, right? And hydrogen would be here. Hydrogen would be here. How about the front one? Now the front, CHO goes down because you flip it 180 degrees. CHO is here, right? When you do this, OH comes here, and hydrogen would be like this. So it's really OH here. Remember what I all did. I just hold OH from back. I just bring it back like this and put it on top. So you have this configuration. So this configuration, I will do the same thing what I did here. So what I will redraw for this would be OH here, right? OH here. That's equivalent to saying that CH2OH is here, right? And here H is like this. H is like this. So that whole group is at the back now. So this OH, OH, CHO is at the back. So you have C, OH. I shouldn't have two OHs, right? One should be, so when I flip this, OH is here. And when I flip this here, OH is on top. And this is H. Sorry, so this is H actually. It should be H. So yeah, I have H, and what else do we have? COH, H, CHO. We have all the back, whatever we have. So OH is here, CH2OH is here, H is here. So now, going priority assignment, one is this one, and two would be this, and three is this, four is this. Now the same thing I did, I have to push the fourth to the back of the board by just rotating this. It would be OH, and bringing group 3 here, COOH, CHO, OH, and the CH2OH will be here, and hydrogen will be at the back. Now, priority 1 is here, priority 2 is here, it's going counterclockwise, so this is S. So the back is S, the front is R. So it is RS. Let me make sure that I have the right configuration. This is R. So flipping it would be by flipping this into the top, OH comes here, CH2OH is here, here, and hydrogen would be here. So priority wise, no, so this carbon had, this is priority 2. I'm sorry, so this is priority 3, because we have the aldehyde group, CCHO, that takes more priority than the alcohol. So now what I'll do is this would go from 1, this is not 2, this is 3, this is 2, so it's going that way. So this is actually R. So both the front and the back are RR configuration. So I'll just write RR. Now we can also assign, based on this, the rest of them actually, to make it much easier. So if you have CHO here, which is CHO here, H and OH are switched in this one, so the front is S in this one. So once you solve one of them, the rest will be much easier. So the front is S in this case. How about the back? For the back, you may not be able to see it now because the back is CH2OH is down here, but CH2OH is up here. So if you just rotate it like that, you can actually solve this. Let's just rotate the back only here. So when you rotate the back to make it to this orientation, to match CH2OH, the back one, if you just rotate CH2OH, OH would come here, H would be here, CH2OH would be here. That means H and OH are switched in this one. Because if you just rotate over the whole thing, OH would come here, H would go there. So would be not here, it would be, for this one, it would be OH and H. So this is opposite of this one. So this is S as well. The back one is S. So this is a mental rotation. And for this one, if you just look at here, CHO, HOH, it's exactly this one. So that would be an S configuration. And if you just look at this one, so for the back one, CH2OH is right there, H is right there, OH is right there, everything is in order. What we have said R for that should be applied for this as well. So it is an R. How about for this one? Now, once you figure out one of them, it is easier to come up with a logical explanation for each one. So CHO-OH H is this one for the front one. So it is an R configuration for the front. How about for the back? The back, I have CH2OH down, right? CH2OH down, but OH is here and H is here. So if I just rotate this to bring CH2OH down here, I will get H here and OH right there. So if you just bring this down here, OH would come here, which is this one, and this H comes here. So the back is the same as this one, because by rotation you can achieve that one. So the back is R actually. So now the relationship is that compound A and compound D are actually the same. RR configuration for A. And SS and SR, these are diastereomeric. So the relationship between A and B, AB, are enantiomers, mirror images, because you have RR, image would be SS, which is AB and ABR, enantiomers. B and C are diastereomers. B and C are diastereomers. Actually, A and D, I would say, they are the same molecules. So what we have is all the relationship is figured out. B and C are, okay, how about C and D? C and D are also diastereomeric. C and D are diastereomers. Looks a little bit complicated, but once you figured out the first initial Newman projection, you would end up just solving it that easily. So the only thing is, as a recap, make sure that you have the Newman projection interpreted as the front OH, CHO, and H on the plane of the board is H and CO. The back is containing all this. So priority assignment is 1 to 2, but you want to send the hydrogen to the back. So I just sent the hydrogen to the back. I have this configuration as R. For the back, that was a little bit tricky. You have to just hold the OH and bring it on the top. So when you do that, OH, CH2, OH would end up here, H would end up here, and the CHO would be here, H would be here, OH there. So now the priority assignment would be, well, that was where I made a little mistake there. So priority 1 is the OH for the front one. 1 is OH. 2 would be not CH2OH, but the whole of the molecule. So 1 is this one, 2 is what is at the back, and 3 would be CH2OH. Then you would figure it out to be an R. So the relationship is important here. AB are enantiomers, BC diastereomers, A and D are same, C and D are diastereomers. I'm sure you'll figure it out on a paper while just reviewing this problem. We'll continue to conclude problems in stereochemistry section of my lecture. This would be our last problem, where we would be looking at optical activity, how to determine enantiomeric excess using measurement of polarimetry. So enantiomeric excess is the measure of how pure, enantiomerically, how pure a compound is. Here as an example I have quinine, which is anti-malarial drug. In a pure form, the RS-SR, which is isolated from a tree, which is used as anti-malarial, has a specific rotation of minus 165 degrees. So it turns the plane polarized to left by 165 degrees when it's a pure compound. So here in this problem, the problem says for you to calculate what's the enantiomeric excess a particular chemist got if he has an optical rotation for his sample, which he synthesized or she synthesized, of that of minus 120 degrees. So the real quinine has given, the enantiomerically pure quinine has minus 165. Actually it's minus 116, let's say. Just to make it easier for us to calculate, actually it must be minus 165, but if you have that and a particular preparation or synthetic product gave you 120 degrees, the enantiomeric excess, or the how much enantiomeric excess you got from our last discussion during the lecture, it is the observed one, observed rotation, observed over the literature value or pure value, literature value for the pure compound. So as I said, quinine has close to 160. This is a minus. That's also a minus. That's a good sign. At least the signs are the same what the researcher found when he synthesized his version of quinine is 120. So minus 120 degrees over minus 160 degrees, the enantiomeric excess is times 100. That would give you 75%. So what this means is that the chemist was able to get 75% pure quinine, pure when I say pure, with this stereochemistry, let's say at least the RS-SR version, which is a pure quinine, he got 75%. So what that means is the rest 25%, which is 100 minus 75, is a mixture of his version, RSSR. If we just say the example, the only mixture he has was the other enantiomer. So the mixture would contain 25% of RSSR. 75% is what he got as excess pure. But that mixture still has 25% of the compound he desired, the quinine, of that and S, R, R, S, let's say the mirror image, the enantiomer. So he has R, S, S, R, S, S, R. So that means 12.5% R, S, S, R in the mixture. That's just in the mixture. 12.5% of S, R, R, S. So this R, R, S is not the desired one. This is the enantiomer, which is opposite enantiomer to this one. But he also, so this mixture is called racemic because it has both enantiomers, mirror image racemics. But the pure enantiomeric excess, what he is desired for in that synthesis, was 75%. So if somebody asks you what total, whether it's in a mixture or as a pure, how much total he got as a quinine, as RSSR, is just in the mixture 75% as pure enantiomeric excess of RSSR, and from the racemic he has about 12.5%. So in the sample the total would be 87.5% total RSSR. As enantiomeric excess, as a pure non-racemic one, he has 75%. But in the mixture, the rest 25% contains these two enantiomers. They are mirror images. Actually, they are called racemic because it's 50-50%. But if somebody asks you what is the total amount of quinine in the whole sample, he has 87.5%, out of which 75% is a pure form of RSSR. So this is how we determine the quality of a product during synthesis or during isolation of a natural product. You use optical activity to calculate the enantiomeric excess from a known literature value. You compare it by taking the ratio and find out enantiomeric excess. With this, we will conclude the section in stereochemistry. In the next lecture 16, I believe, I will continue about organic reactions and different mechanisms and energetics of a reaction, kinetics, and the likes, thermodynamics as well. So I would like you to share and subscribe to the channel, and also give me your comments in the comment section so that I can address some of your questions in the comments. Thank you for listening. Continuing our discussion, I'd like to say a few words on sugar stereochemistry. We haven't covered in the lecture, but I'd like to show you what a Fischer projection is. Fischer projection is you have a vertical line and horizontal substituents across the vertical line. So, for example, this is Fischer projection is mostly applied in sugar chemistry. It starts from the simplest molecule, diglyceraldehyde, is when you have the aldehyde portion as carbon 1, CHOH is in the middle, OH is to the right, and this is the alcohol form. So if you were to draw a D-glucose 4, D refers to 5 position, the OH is the same as that one. So that's the D configuration. You have carbon 1, the naming starts from carbon 1, 2, 3, 4, 5, 6, and at carbon 2, 3, 4, 5, all are stereogenic centers. So mostly, even though we present sugars in a Fischer projection, a vertical line and horizontal lines. Most of the sugars exist as cyclic form. For example, you have the D-glucose has two forms. That means this OH make a bond with this carbon right there to form a new alcohol, which is this alcohol. But the rest of them, relative to the other, remain in the same configuration. So 2 position is an R configuration, 3 is an S configuration, 4 is an R configuration, 5 is an R configuration. The way you would reduce this into such kind of structure would be all of the vertical lines are assumed to be going to the plane of the board, and the horizontal ones are coming towards us. So if you just bring back this from going back and bring it back this way, or also rotate it to the left, you would end up having this structure. That means the ones which were back to the plane of the board would be on the plane of the board, while the H, OH and H would be in and out of the plane of the board. So basically OH was brought to the left, it is here, and H is going down. So each one of them are assigned, just doing at each carbon you would have such configuration and assign priority. So if you have assigned priority, here is 1, here is 1, this is 2. So if you just go this way, this is an R configuration. So at each carbon position we have determined this to be a 2R, that's 2R, 3S, 4R, 5R. So as I said, most of the glucose actually is in a cyclic form, but when this goes and make a bond with this carbon, the OH that is being formed will be either down or up. So when it's down, it's called alpha D-glucose. When the OH is up on the surface of the ring relative to the others, this will be a beta. So mostly there is alpha and beta mixture in D-glucose. So that's why we use optical rotation to determine what's the proportion of the alpha form and the beta form. For example, in this problem, the sample of D-glucose is dissolved in water, which showed 57 degrees optical rotation. But the pure one, pure alpha, is 112 degrees, but it shows 57 degrees. So it's asking you what is the enantiomeric excess. Enantiomeric excess is defined as the enantiomeric excess percent equals the degree that is observed rotation over true value, pure or literature value. So in our case now, if the alpha is the most dominant one, that's the pure one, I'll just put 112 or 57. So 57 degrees over 112 degrees. So this would give us about 51, I believe, close to 51. I'm not entirely sure. So the enantiomeric percent is 51. There's times 100, so 51. Now, the next question is, it's asking you what is the alpha D-glucose, the total alpha D-glucose in this sample. So the total alpha D-glucose would be, first of all, the enantiomeric excess is 51%, which is purely the alpha. Now, the racemic mixture of alpha and beta is the remaining one. So 49% would be a beta and alpha and alpha. That's racemic. That means half of this 49 is half of that would be 24.5% alpha, 25.5% beta. This is the racemic mixture. So in the total amount of each one of them would be, so the alpha would be the pure form, which is enantiomerically excess, which is 51, and from the mixture you get about alpha is 24.5. So alpha total, alpha glucose, alpha D-glucose, total, I would say this is total, is 51% from pure, and from the mix you would get 24.5. So the total would be 75.5% is alpha D-glucose. So if you just dissolve some amount of D-glucose, this D-glucose, the mixture would contain about 75.5% is alpha, the rest about 24.5 is beta D-glucose. So these are the type of stereochemical application when it comes to sugar. So I want you to exercise more on Fischer projection and how you start to have the R and S assignment and know the difference between alpha D-glucose and beta D-glucose. This is only that hydroxy group is what's determined the alpha and beta. The rest is the same. So this is OH down, that's an alpha. OH up is beta D-glucose. So these are mostly the stereochemistry that's found in sugars that you need to understand. One more biologically important molecule which has several stereogenic center. It's called cholesterol. I'm sure most of you know. This is the chemical structure of cholesterol. It's a steroid, or a steroidal molecule with several stereogenic center. It has the pure cholesterol has a specific rotation of -32 degrees. That means it's active. The polarimeter measurement or gives you an active optical rotation of -32 degrees. So in this problem you have to assign or just locate stereocenters. So I will begin with looking at the compound from carbon 1. Carbon 1 cannot be a stereogenic center. 2 is not, obviously. There are 2 hydrogens on it. But carbon 3 is a stereogenic center. Carbon 4 is not. Carbon 5 is not. Carbon 6 is not. 7 is not. Carbon 8 is a stereogenic center. Carbon 9 is a stereogenic center. Carbon 10 is a stereogenic center. When you go to carbon 11, it's not. 12 is not. 13 is not, is a stereogenic center. 17 or 14 going down here sequentially is a stereogenic center. 15 is not. 16 is not. 17 is a stereogenic center, and now 20 is a stereogenic center. Obviously 18, 19 is CH3. CH3 cannot be a stereogenic center. Now if we were to count the number of stereogenic center, at least would have about 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So cholesterol has 8 stereogenic centers, chiral centers, which suggests that there are 2 to the power of 8, which is 256 different stereoisomers. Out of those, I believe the only biologically active cholesterol, one which is found in our bodies, and the other would be, I think, mostly synthetic, are 2. So out of 256 stereoisomers, cholesterol, which is stereospecific one, has an alpha rotation of -32 degrees. So I want you to assign the R and A's when you are at home. So I'll just give you the stereogenic assignment, and you must prove or check that the assignment is right. So we'll start from 3s, 8s, I have assigned those, 9s, 10r, 13r, 14s, 17 is R, 20 is R. For example, if I were just to pick 3 as S, the way it was done is, this is priority 1, obviously. Priority 2 would be going this way or going that way. So it depends which way we should go. This is same, this is this carbon, but here you go to this one. So priority number 2 is this, priority number 3 is this side of the carbon. Obviously hydrogen is implied, it is down, so going from 1 to 2 is an S. So this is correct. So priority 1, priority side is this carbon side, not that one, because if you just continue, this and this are equal, but this and that are not equal. This has more denser carbon to carbon. This is 2 hydrogens. That's why this would get a priority 2. So just by doing for each one of those, you could be assigning those stereochemistry. So very elaborate molecule. That's why it has a good biological implication. And the stereospecificity is, for a pure cholesterol, the optical rotation is -32 degrees. With this, I think would be finalizing assigning stereogenic center and chiral center for biological molecules.